Okay, hi everyone, and welcome to Video Notes 8.7, where we're going to talk a lot about exponential functions. In part 2 or day 2, we'll talk more about the graphing. But today we're going to focus on exponential functions, kind of just the general parts. What do they look like? So to do that, really, since we don't know anything about them, is to look at a linear function. We're pretty comfortable with a linear function, so let's start there. We know what it looks like if we're given a table of values. It looks like this. We know a little bit about its general form, slope-intercept form, right? So let's look and compare this. So let's explore this particular linear function here on the left, and then we're going to compare that to the exponential function on the right. And again, what are we looking for? Well, we're looking to see if we can see the growth in a table. We're looking to see if we can see exponential growth in a table. We should probably name it. Can we see it all the time? How do the graphs differ? So those are some of the things that we're looking for. So if we were given this table of data, we wanted to look at it as a linear function. The first thing we'd probably do is take the differences between our y2 and our y1 and then compare them to the differences on our x2 minus x1. So let's go ahead and do that. From 3 to 6, the difference is 3, and over here is 1. And then we're going to continue this process for the next 2 points. So we're going to take 9 and compare the difference between that and 6, which is 3. And then over here on the other side, 3 minus 2 is 1. What you're going to find for all of this table, if I pause it and let you work it out, is that you're going to find that this is constant. This change between our values, our y values, as we move along our x values here. If that's constant, we verify that it's a linear function. Okay, that means it's a linear function. What did we find? Well, what we found was slope, because that's essentially what that is, right? Calculating slope between 2 points, and if it's constant, it means that between every 2 points is the same slope, meaning that it is a linear function. We could also tell by looking at this, since 3 is our slope, that the slope is positive, increasing from left to right. Right, so it's got a positive slope. We know that it's going to make a line because we have that constant rate of change. So now that we've got our linear function, let's take a look at our exponential function here. So same thing, we're going to compare these two. This is us taking what we call, I don't know if I labeled this is what we call the first difference, right? So we're taking the differences or subtracting our points, and we find that the first difference is constant, meaning a linear function. So let's do that over here. So looking at these values, we're going to take the first difference. 2 minus 1 is 1, and 9 minus 3 is 6. 27 minus 9 is 18. 81 minus 27 is 54. But you'll notice that this is not constant. Really, these values are getting bigger as we move along, meaning that there's a larger increase each time we go along the x-axis. Our y values are getting farther and farther apart. That's what an exponential is. It's not a same value as we increase, it increases each time. Well, what does that mean to the graph? I mean, if we look at a linear one, right, it's the same amount each time we go over an x value. But since these are getting larger and larger and larger, what we should see is a curve. And what we'll find is it's going to be the steepest of curves, because it's really going to take off at some point and make this large increasing sweeping curve, because the values of the y are getting larger and larger each time. So how do we see if this is exponential in a table of data? Well, we can do that. We just have to do it a different way. What we're going to do is we're going to go ahead and name it as well. We're going to find the common ratio. And the common ratio means that we're doing a division, right? That's what ratio stands for. Fraction, ratio, those are the same thing. So we're doing a division essentially. We're going to start dividing our 2 points instead of subtracting them. And what we should find here, let me change my color so I'll stand out a little bit. What we should find is 9 divided by 3 is 3. And we're going to take 27 and divide that by 9, which is 3. And we're going to take 81 and divide it by 27, and that's 3. If this is constant all the way down, just like we saw before on the linears, then we can verify that this is an exponential function. Okay, and that's what we call a common ratio versus a first difference. So now we have a way to see a set of data if it is an exponential function, and we've also got a way to see if it's a linear. So now that we've kind of got an idea of what the shape is and how to verify them, let's go over here and summarize all of what we know about linears and exponentials. Okay, so a linear function, we'll start there because we're more comfortable with them. The y values are going to have a constant rate of change. if you will, a slope between them, right? How do we find that? Well, we take the first difference, which is just a slope calculation. If that's constant, verifies that it's a linear function. What shape do we get with the linear function? Well, if the slope is positive, it increases from left to right. If it's a negative, it decreases from left to right. And an example of a linear function would be something like this. Some value per, right? One of the words that we see is per or multiplication. We should see our variable multiplied to some value or not, doesn't matter, and there may be something added to the side or subtracted, but that's a general shape of it. So let's compare that to exponential then. We saw that the values between the y are increasing as we go. So it's not a constant, it's increasing. It's getting larger and larger and larger. Well, how do we identify that? Well, we take a division or ratio of those two values, right? Take the previous point, or take the point and divide it by its previous point. If that's constant, it verifies that it's exponential. All right, well, what does that mean to the shape of the graph? Well, that means that we should have a curve that gets very steep very fast if it's positive or increasing. If it's not, we may see that that curve starts really, really fast decreasing and get really close to something and smooth itself out. So, and we'll explore this in a little bit more. We'll talk about all the forms of the graphs. But what does an example of that look like algebraically? Well, that looks like this. And the key to this is that your variable should be an exponent. Okay, that's the key. Okay, you want to see that. You don't want to see any other exponent besides a variable there. That signifies it algebraically that that's an exponential function. All right, so let's go back over here and continue on with our notes. So linear functions have a constant rate of change. Exponential functions have a common ratio, and we saw that on the side over there. Make sure that you write that down. So let's explore its base form. So what does an exponential look like in this base form? Well, we're comfortable with a linear one, right? Y equals mx plus b, right? That would be, we know that that's slope, and we know that b is our y-intercept. So what does an exponential look like then? Well, this a value is kind of your b. There's a relationship there. B is our y-intercept, right? Our initial value. So is our a. In an exponential, our a value, whatever's out front multiplied, and we'll talk more about this in a second, multiplied to our growth factor, is our initial amount or our y-intercept. Sometimes, just to make sure that you see this, you're going to have parentheses here. A lot of times your growth factor, or how much it's increasing by between the y values, right? So this is going to be how much it's increasing. It should be increasing as we go along. Is going to be inside parentheses. That's going to be the part that's raised to the exponent. That's really how you signify it. If that's the base, and this is raised to that exponent of x, right? And this should always be an x. That should be our input. Y should be our output. So the growth factor then, if it's greater than 0, or I'm sorry, greater than 0 or greater than 1, if your growth factor b is greater than 1, it's going to be a growing, okay? It's a growth. We'll talk more about this in a second. If it happens to be a decimal, meaning that it falls between 0 and 1, it's going to be what we call a decay. Okay, and we'll go through that in a second. But there's two forms of this. There's a growing one and a decaying one. All right, so now we've kind of got the base form here. We need to pay attention to our input. Our input for other things is a little bit more straightforward, but we need to be cautious with this one because sometimes our inputs are number of periods, when events happen, or when do changes take place. I just want to call a little bit of attention to it so you take your time, and you'll see that in one of our examples down here at the bottom. All right, but now let's move on then and say, hey, let's see if we can identify some of these exponential functions. Well, let's look at this one here. We see we've got a base. We see this caret key. And we know that the caret key signifies an exponent. So if we rewrite this, it should look something like that. The base of 2 raised to the x, which looks just like our form up here. So is it exponential? Yes, it is. What is our a value? Well, this is our base or exponent. So we know that that's our growth factor and our exponent. But where's our a? Well, if it's not written, we know that it's a 1 multiplied to that. So in this case, our a is 1 and our growth factor is 2. All right, so we're looking at this exponent here. We've got an a value, possibly, right? We've got an x here, but we're concerned because we said our exponent should be in the, or a variable should be in the exponent location, and you'll notice that it's not. But we do have an exponent. Don't get confused here. This is not an exponential, okay? This is really kind of along the lines of a quadratic or a polynomial, but we're not going to explore that. So this one does not fit our value of exponential, so there is no a or b. Looking at the next one, though, we can see we possibly have an a value here. We seem to have a base, and it's raised to an x. It doesn't matter that it's a negative. Our variable is in our exponent location. So let's identify the parts. Our a is -4. Our growth factor on this one is 2.6. All right, So now we've seen what some exponentials look like and we can identify them. Let's see if we can go ahead and model one and maybe do some evaluation so you can see what that looks like with exponentials. All right, so we've got an island of rabbits here. There are 20 rabbits as our initial amount. So we already automatically know that that's our y-intercept. It says that the rabbit population triples every half year. So we're going to pay attention to this, but let's get this piece of information out, which is that the growth factor is tripling. Okay, so if you look over here, here's the tripling, and here's our initial value of 20 rabbits. Our exponent, our variable, is our exponent, so we're doing pretty good. But we need to figure out what that value is going to be because it's also an evaluation. So they've given us the function. So let's go ahead and write that out. They've already done the modeling for us. That's okay. We'll practice that on our own in a little bit. Let me use parentheses here. But we need to figure out this value here, our t. So our t, as it says, it triples every half year. And this is where I said to be cautious of this. But it's over a 2-year period. So what we're really looking at is we know that it's 2 years, but there's 2 occurrences in each year. So we're going to have to multiply that by 2. So our number of changes over the 2 years, and again, I said be cautious with that. That's why we want to be very careful. The number of changes over 2 years is actually going to be 4. So some of us would rush and throw 2 in there really quickly, and we need to make sure that we don't do that. So if we do that quick little calculation there, we're going to find out, we put that into our calculator, you'd want to do it in chunks, so you probably want to take 3 to the 4th first, and then multiply it by 20. What you're going to find out is that it's going to be 1,620. Okay, so we need to put this in words, so the number of rabbits in 2 years will be 16,020. Okay, so that's a little modeling, a little evaluation at the same time. You'll see that in your homework. But let's talk about just some straight evaluation. So this one is evaluate, which means plug a number in, get a number out. Here's our function here, right? Make sure that you check this one out on your own. So here's our function here. It says we've got some domains that we want to input. And we remember then that domains really just means a set of x values. So we've got an x value of -2 we're going to plug in, an x value of 0 that we're going to plug in, and an x value of 3 that we're going to plug in. So we're quite literally just going to plug them in and chug them out, right? Plug a number in, get a number out. So I'm going to go ahead and put my base of 5. My exponent this time is going to be to the -2. Good thing we've got our exponent properties because we remember that if we have a base raised to a negative exponent that it tells us to move its position. So this is going to become 1 over 5 squared or 1/25. Okay, so let's do the next one there. So y equals, we're going to plug in 0 this time, so 5 to the 0 power, which everything to the 0 power is 1, so I'm going to shoot this over so they're all lined up. And then we're going to do the last one here, which is 3, so 5 to the 3rd power, or 25 times 5, which is 125. And again, I'm going to shoot it over just so we have a line of them. Okay, so what we see is that these right here are our ranges, right? These are, if this is a domain, right, an x value, we put it in, we get a range out or a y value out. So that really kind of is asking us to go ahead and line it up and say, what are our ranges for this? I mean, that's really what that question is getting to. So we're going to say a set of ranges are 1 over 125 and 1 and 125. Again, decreasing or increasing order, so smallest to largest. And that's what that question is asking about. So that's our notes for today. Let's go ahead and review really quickly. We've got exponential functions that have increasing values between their y values as we go along in x. They have a common ratio, a division of our y values. If that's constant, it confirms that it's exponential. Should have a large sweeping curve or a sweeping curve that's decreasing as we go, right? We know that this is going to be values that are decimals, and these are going to be greater than 1, okay, so larger than 1. And we know that there should be a base, and our variable should be in that exponent position, okay? And we've seen it evaluated. All right, so that's everything for this section of notes. We'll see you in the next section. All right, have a good day.